What specific problem does the new method or algorithm aim to solve?
The new method or algorithm aims to solve the problem of understanding the behavior of transformer-based large language models, LLMs, with billions of parameters by investigating the role and necessity of individual layers within the models. The method explores questions such as whether all layers are necessary, if middle layers perform the same function, if the layer order matters, and if layers can be run in parallel. By conducting experiments on pre-trained LLMs like Llama 2 and BERT Large, the method aims to provide insights into the shared representation space of middle layers, the impact of skipping or looping layers, the importance of layer order, and the potential for parallel execution of layers. The goal is to gain a deeper understanding of how these models operate and potentially optimize their performance by identifying redundant layers or exploring more efficient execution strategies.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method or algorithm works by first testing whether different layers in the transformer models share a common representation space. This is done by skipping specific layers or switching the order of neighboring layers to see if the models are robust to these changes. The experiment results show that middle layers share a common representation space and have distinct representation spaces from the outer layers. Next, the algorithm tests if all layers are necessary by skipping layers and observing the performance degradation. The results indicate that at least a few middle layers can be dropped without catastrophic failure. The algorithm then investigates if middle layers are performing the same function by replacing the weights of middle layers with those of the center layer and looping on this layer multiple times. The results show that sharing weights among middle layers is catastrophic, indicating that the middle layers are performing different functions. Additionally, the algorithm explores the impact of layer order by running middle layers in reverse order or in a random order. The results suggest that layer order somewhat matters, as both randomizing and reversing the middle layer order show graceful degradation. Finally, the algorithm tests if layers can be run in parallel by executing middle layers independently and merging their results. The results show that running layers in parallel can be beneficial for most benchmarks except for math-heavy tasks. Additionally, the algorithm investigates if looping parallelized layers can improve performance, with results indicating that looping the parallelized layer multiple times can enhance model performance.
What are the theoretical or practical benefits of using this method?
The theoretical benefits of using the method described in the paper include gaining insights into the behavior of transformer-based large language models, LLMs, by understanding how the layers operate and interact within the model. This method allows for investigating whether middle layers share a common representation space, determining the necessity of all layers, exploring if middle layers perform different functions, and assessing the impact of layer order on model performance. Practically, this method can help in optimizing model architecture by potentially reducing the number of layers without catastrophic failure, improving efficiency by running layers in parallel, and understanding the importance of layer order for different types of tasks. Additionally, this method could lead to developing more efficient transformer models with lower latency without significant loss in performance, which could have practical implications for real-world applications where computational resources are limited.
How is the method validated or tested?
The method is validated or tested through a series of experiments on pre-trained large language models, LLMs, specifically Llama 2 and BERT Large. The experiments include variations on the standard transformer execution strategy, such as skipping layers, running layers in reverse order, running layers in random order, and running layers in parallel. These variations are tested across a variety of benchmarks for both decoder-only and encoder-only models. The impact of these variations on the model's performance is measured without fine-tuning the model's parameters, except for the BERT evaluation, which includes a standard fine-tuning step. The experiments aim to address questions such as whether layers share the same representation space, if all layers are necessary, if middle layers perform the same function, if the layer order matters, and if layers can be run in parallel. The results of these experiments provide insights into the behavior of the middle layers of the transformers, and how different variations affect the model's performance on various tasks.
What results were achieved with this new method?
The results achieved with the new method include the discovery that middle layers in transformer models share a common representation space, allowing for graceful degradation when skipping or rearranging layers. It was found that a few middle layers can be dropped without catastrophic failure, indicating that not all layers are necessary. Additionally, it was observed that sharing weights among middle layers is catastrophic, suggesting that these layers perform different functions. The study also revealed that the order of middle layers somewhat matters, with randomizing or reversing the layer order showing graceful degradation. Running the middle layers in parallel was successful for most benchmarks, except for math-heavy tasks. Furthermore, looping parallelized layers improved performance, with the optimal number of iterations being proportional to the number of parallelized layers. Overall, the least harmful variants were found to be randomizing the layer order and looped parallel, while repeating a single layer was the worst performing variant.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method presented in the paper include the fact that the experiments were conducted on pre-trained large language models, LLMs, without fine-tuning or adjusting the model parameters, except for the BERT evaluation, which included a standard fine-tuning step. This limitation may affect the generalizability of the findings to models that have been fine-tuned or modified in some way. Additionally, the experiments focused on specific transformer models, Llama 2 and BERT large, and may not be directly applicable to other transformer architectures or sizes. Another limitation is that the study primarily investigated the behavior of middle layers in transformers and did not extensively explore the impact on other parts of the model. Furthermore, the paper acknowledges that a full explanation for why transformers are robust to the variations tested is left for future work, indicating that there may be gaps in understanding the underlying mechanisms driving the observed results. Lastly, while the experiments provided insights into the behavior of transformer layers using the layers as painters analogy, the paper does not delve into the practical implications or applications of the findings in real-world scenarios.